In order to talk about imaginary numbers and complex numbers, we have to have some definitions first. So I is the square root of -1, and there's a really good video made by Welch Labs that talks about where imaginary numbers come from, and I'm going to put that link in the description below if you want to check that out, but for our purposes, this will be enough to get us going. So imaginary units are just the smallest bit here, just I by itself. That's the square root of -1, and they're calling these pure imaginary numbers, a small little set of numbers. And then there's a bigger set of numbers, imaginary, that encompass that. And then actually complex numbers is this entire set of numbers that we've always been dealing with our whole life. Like even like natural or counting numbers like 1, 2, 3, or integers, those are all considered complex numbers as well. And here's why. So in general, a plus bi is a complex number. And it looks weird because there's two pieces to it, but it's just one single number. So in this complex number, we call a the real part because it's just some real number, and then bi, that's the imaginary term. So it goes through these three examples here. It just says if b is 0, then the complex number is a real number. Well, if b was 0, that means that this imaginary thing would just go away and you'd just be left with a. So yeah, of course it's going to be a real number. So then as long as b doesn't equal 0, we're going to have something called an imaginary number. It's going to look like a plus bi. There's going to be two parts to it. And then the last one says if a is 0, that means that this would just go away and you would just have this imaginary part, so we call that a pure imaginary number. Alright, so let's get into some actual problems. We can figure out what I to many different powers are actually really easily. I just rely on two facts. So you do have to remember that I is the square root of -1, and then, well, if you were to square both sides to figure out what I squared is, you would just cancel the square root and the squared, right? So I squared is just -1. Those are two really important facts, and then from there you can figure out any other power of I. Like if you had I cubed, you could just think of that as I squared times I. Well, I squared is -1, and I is just, we're just going to write that as I. You could write that as the square root of -1, but I don't think that's simpler. I think it looks nicer like this. And actually, let's write it even nicer. Let's just write -I. So it's weird, but I cubed is the same thing as -I to the first power. Okay, I to the fourth power, we could think of that as I squared times I squared again. Well, I squared is -1 times -1, that would just be +1. So I to the fourth is the same thing as +1. So again, for the rest of these, I'm just using these two facts. So I'm going to build everything up just using I squareds and I's. So I to the fifth, well, I could build that up with I squared, and then another I squared. Well, that gives me 4, so I just need one more. Well, this would be the same thing as -1 times -1 here, right? So that would just be +1, and then times I, well, that just means I. So I to the fifth could be simplified down to just the same thing as I to the first power. Alright, I to the sixth, I'm going to do this a little bit different. I'm still going to use just I squared, but instead of multiplying by a bunch of different things, I'm going to think of it this way. I squared to the third power. Because now it's really simple. I squared is just -1 to the third power. Well, a negative to an odd power stays negative, so that's just -1. And I could do the same thing for I to the seventh. That would be like I squared to the third. Well, that would give me 6 of them, but I still need one more. Oops, so times I. Well, that would be, well, we said I squared to the third. That was the same thing as -1. So -1 times I. So this is just -I. And the last one, I to the eighth. So I can think of that as I squared to the fourth. Well, that's -1 to the fourth power. So a negative to an even power is just a +1. And you might actually be seeing a pattern now. So I to the fifth was the same thing as just I to the sixth was the same thing as I squared. I to the seventh was the same thing as I to the third. And I to the eighth was the same thing as I to the fourth. And this pattern will continue forever. So to save ourselves some time, we can see that I to the ninth would be the same thing as I to the 10th would be the same thing as -1, I to the 11th is the same thing as -I, and I to the 12th can simplify down to just 1. But again, in practice, when I'm doing these problems, I still just use I and I squared. So if I have to build up I to the 63rd, I'm going to think I squared, well, how many times will that go into 63? Well, it could go into 60, that would be 30 times. It could go into 62, that would be 31 times. And I just need one more I to get all the way up to 63. Alright, so I squared is -1 to the 31st power, so that's odd. That means this is going to stay negative times this I. So just -I. Alright, in this next one, I'm going to put I squared to some power. So I'm going to try to get to 57. Well, I know I could get to 56. 56 divided by 2 would be 28. And then I just need one more I to get all the way to 57. So this is like negative 1 to the 28th power, and that's a negative to an even power, so this is going to be positive now. So the final answer is just positive I. 104 is an even number, so I squared can go into that. It's going to be 52 times, and I don't need any extra i's after that. So I squared is negative 1 to a 52nd power, that's even, so this is going to be a positive number, so just positive 1. Alright, and then finally for the biggest one, I to the 330th power. Well, again, just think of it as I squared to some power. So 330 divided by 2 would be, let's see, 150, and we got to get 30 more out of that, so 165. And all that matters is this is negative 1 to an odd power, so it's going to stay negative. In the next set of problems, we're asked to simplify the complex number, and then it says write it in standard form. So just remember that standard form means a plus bi. We want to write the real part first and the imaginary part second. So looking at number 5, we start with 2i. There's nothing to simplify there, but now I see I cubed. And we saw before that I can rewrite I cubed as I squared times another I. And that would be the same thing as negative 1 times I, so just negative I. Alright, that means that this is like negative 6 times negative I. That means that altogether it's going to be positive 6. So this thing simplifies to positive 6, and then I have 2i, and I'm going to write that second so that this is in standard form. In number 6, I've got two different terms with I to big powers, so let's simplify those first. I'm going to think of this as I squared. Well, I could get up to 14 by raising this to the 7th power, and then I just need one more I. Put a 3 in front of that, and then over here, put the 4 down first, and then I squared. I could get all the way up to 18 by raising this to the 9th power. 2 times 9 is 18. And then again, I just need one more I. Alright, so this is negative 1 to an odd power. That's going to be a negative number. So negative 3, and then this I just comes down. Again, negative 1 to an odd power is going to stay negative. So this is negative 4, and then the I just comes down again. So I have negative 3i minus 4i. That's the same thing as just negative 7i. And there's no real part here, so I can just leave it as this. I don't have to try to rearrange anything to write it in standard form. I can just leave it as negative 7i. It's a pure imaginary number. Here we get into actually multiplying complex numbers together. And I like to use the box method anytime I'm multiplying binomials together. So for number 9, I'm just going to write it out like this. I'm going to write the box right underneath the second factor, and then just put 3 minus 2i on the side. So 3 times 5 is 15. 3 times 3i would be 9i. 5 times negative 2 is negative 10, and then there's an I. And now 3 times negative 2 is negative 6. I times I is I squared. Okay, well with this box, I squared is negative 1, so this box altogether would be the same thing as positive 6. Now I just have to combine all the like terms in that box. So 15 and 6 will go together, and that would make 21. And 9i and negative 10i go together, that would make negative I. And that's in standard form because I have the real part first and the imaginary part second. Let's do the same thing for number 10. So I'll draw the box right underneath the second factor and put 17 minus 3i on the side. Alright, 4 times 17 is 68, and 9 times 17 is 153, so negative 153i. Alright, 4 times negative 3 is just negative 12i, and then negative 3 times negative 9 would be positive 27, and then I squared. So that last box is really negative 27, and when I combine that with the 68, I get 41, and now I just have to combine these I terms together. So that would be negative 165i. In number 11, I just have to distribute this negative 8i into the parentheses. So I'm going to have negative 32i, and then negative 8 times 3 is negative 24, and then I'm going to have I squared. So now I just have some rearranging to do because I squared here is negative 1. That makes that term the same thing as positive 24. Now I'm just going to put the negative 32i second so that it's in standard form. This last one is kind of a special case. You'll see why in a second. When I multiply these, I'll put the box under the second binomial term again, and we'll have the square root of 7 plus 3i on the left side. Okay, so I'll multiply these together, and the square root of 7 times the square root of 7, it seems kind of messy, but it's the same thing as like squared. It's times itself. So the square root and the squared go away, and we're really just left with 7. All right, and then this would be negative 3 square roots of 7i, which is really ugly. But then this box is positive 3 square roots of 7i. And that's great because these just cancel out. And then 3 times negative 3 is negative 9, and then I squared. So again, that last box is the same thing as positive 9 because I squared is negative 1. So now when I combine the 9 and the 7, I just get 16. It's just a real number for my answer. All of the imaginary part canceled out. So that happened because these are considered complex conjugates. They're the exact same complex number. The only difference is this one is plus and this one is minus. So we just changed the middle sign. That's what this definition says here. We just have a plus bi and a minus bi. We call those complex conjugates. Normally they would just be called conjugates, but because they're complex numbers, we call them complex conjugates. So these problems, it says find the conjugates of the given complex number, then find the product of the number and its conjugate. So 13, we actually start you off with kind of a weird one because we can't really take the square root of 3. So the square root of negative 3, I'm just going to change this into like the square root of negative 1 times 3. So this part of it is just I. So this is the same thing as I square roots of 3. And notice that I'm writing the I on the left side of the square root because if I wrote it as the square root of 3 and then I over here, it's a little confusing if it's outside of the square root or if it's inside of the square root, so it's just better to write it this way. And again, this is weird because there's no real part to this. There's no a, so it's really like this says 0 plus I square roots of 3. So the conjugate would be 0 minus I square roots of 3, but I'm not going to write the zeros in front, so the conjugate is just negative I square root of 3. So now let's multiply these together. I'm going to write I square roots of 3 times negative I square roots of 3. Alright, so I times negative I, that gives me negative I squared, and the square root of 3 times itself just makes the square root go away, and this is just 3. So altogether, well, wait, I squared was negative 1 times negative in front would be positive 1, so this is just positive 3. Number 14 is a little bit more of a standard looking problem because this is a complex number in standard form. We have a real part and an imaginary part. All I'm going to change for the complex conjugate is the middle sign. So it's still going to be negative 9, but minus 2i instead. So now I'm going to multiply these together, and I'm going to use the box to do that. Negative 9 times itself is positive 81. This would be negative 18i, and this would be positive 18i. Again, these are complex conjugates, so these should cancel out. I expected that to happen. Negative 2 times positive 2 is negative 4, and then this is I squared. I squared is negative 1, so this last box is really positive 4. And when I combine that with the 81, my final answer is just 85. It's just a real number. We're going to end the video with dividing complex numbers. So it says perform the indicated division and write your answer in standard form again. The way we do this is we're actually going to multiply the entire fraction by the conjugate of the denominator. So in number 15, the conjugate of the denominator, 1 plus 2i, would be 1 minus 2i. And I can't just multiply the bottom of a fraction. That's going to change this problem. In order to keep the problem, like the value of this thing the same, I have to multiply the top and the bottom of that fraction. The reason it's okay to do that is because this factor divided by itself is the same thing as just 1. And multiplying by 1 is totally okay. So when I do this, I'm going to distribute the 5 through. So this would be 5 minus 10i. Now on bottom, okay, this is going to be a little bit more complicated. So I'm going to draw a little box method problem out and put 1 plus 2i and then 1 minus 2i on the side. All right, so this is 1, 2i, negative 2i, those cancel, and then negative 4i squared, which is actually, this is all just positive 4. So 4 and 1 go together just to make 5. And this looks great except for it's not in standard form yet. I want to split it up so that it looks like a plus bi. So I'm going to write 5 over 5 minus 10 over 5 I. And then of course I can simplify that. 5 over 5 is 1, 10 over 5 is 2. So my complex number in standard form is 1 minus 2i. And that's an important result because that means we can take an ugly number like this with a complex number in the denominator and we can change it into a bit of a better looking complex number like this. We're going to do the same thing for number 16. So the bottom, the conjugate would be 3 minus I, and I'm going to do that on top too, 3 minus I. So I'm going to have to set up 2 box problems for this. Here's the numerator. So 12 and negative 3 go together to make 9, and negative 4i and negative 9i is negative 13i. So now let's do the same thing on the bottom.